Namaste and welcome to Apna Gurukul, one step towards your success. And this, and today we are starting a brand new chapter that is called Number System. This is based on the NCERT textbooks. ICSE and all the other syllabus will be doing later. Let's start with Number System NCERT. So before we start, I just want to ask you all, are you clear with numbers? These are very, very basic questions, but still I would ask because these are the things required to understand this chapter in detail. Number thing, numbers. Are you clear with number line? The number line which we played on and which we discussed how to operate with number line. I hope you remember that in class 8th and class 7th. You might have already discussed that. Basic operations. What do I mean by basic operations is addition, subtraction, multiplication, and division, and some a little bit about square roots. I hope you are clear with those basic operations. And then the basic geometry. Now, in this basic geometry, I mean, are you clear with how to use the protractor, how to use scale, how to use the compass, how to draw a circle with a compass, and all similar basic geometry parts? And I hope you are clear with. If you are clear, you can just say yes to yourself because that matters a lot. Or you can just comment a yes or yes so that we can stay aligned together and learn something new every moment. And what are we going to learn in this chapter? Let's take a look at that. So learning in this chapter will be, first thing which we will learn about is number systems and their properties. And then we are going to learn about irrational numbers, their definition, the explanation, how do we represent irrational numbers on the number line. And then we are going to read about real numbers and their decimal expansions. And then we are going to read about terminating, recurring, non-terminating, non-recurring, all the types of decimal expansion that will have lots of new terms which will be introduced for you, but we will try to understand it in detail. And then, as we discussed, representing real numbers on number line, we have two methods, one square root spiral, and then we have one more method. We will understand and then we will prove that as well. That's another fun. And then we will try to understand the operations on real number line. And what do I mean by operations is, now, operations, the addition, subtraction, multiplication, and division, and square roots, we will try to understand it on real numbers. That's very much important. So far, we only have studied till rational numbers. First of all, we will try to understand what exactly is a real number also. And then we will understand law of exponents for real numbers as well. Okay, so I hope you are excited for this. Let's begin the chapter with a wonderful quotation. Maths is fun when we practice it enough. If we do not practice maths, it becomes very, very lethargic, and that is why most of the students hate mathematics. So we will start this beautiful, amazing discussion with a beautiful number story. All of you are fascinated with the stories, and I have brought you the number story, and this will be really, really awesome for you, and we'll have lots of fun. So let's begin. So now, number story begins with beginning of numbers. How did numbers began? So in the old ancient days, we started collecting things. Now, when we started collecting things, our ancestors, there should be some method to count it, right? There should be something so that we can understand how much have we collected. So when that need came, then we started counting numbers, and that's how the natural number was born. And natural numbers are simple. That's why it is also called as counting numbers. And then we had addition and subtraction of numbers. And how did we get to know about that? When we were collecting things, somebody gave us something or somebody took something from us. Now there should be something some process we must have to count it, to have a calculation towards it. And that's how we started to develop addition and subtraction. But then suddenly a thing came in mind. What if whatever we had, somebody took it away and we are left with nothing? How do we represent that? So there came the discovery of zero. And the zero, when this zero was discovered, we named the number system as whole numbers, which included zero as well as natural numbers. We must understand one thing, that whenever we move to a new number system, it's not that the old number systems are deleted. It's always extension of number system. So now we had whole number, and Aryabhatta, the great Indian mathematician and philosopher, he is credited with the discovery of zero. And that's how we reach to whole numbers. Now, as these civilizations progress, as the societies started to develop, we had certain need of money, because when the counting started, we had certain exchange system and some currencies started to come. Then there was a zamindari system, and during those days people started to borrow money. Now what if we have nothing and we borrowed some money? Actually, that money is not ours. We are in debt. So to represent the debt, there came new numbers which are called as negative numbers. So what happened now? Negative numbers plus the natural numbers and the zero, collectively they started to be called as integers. And after integers was done, it was named as Zelan. The integers was supposed to be developed by German mathematicians, and the work was going on Germany. So Zelan in Germany means to count. So in that particular days, it was believed that these numbers are enough for us to count anything, and that's why it was called as Zelan. And that's how the symbol of integers is given to be Z. That's the reason. So Zelan is written Z for Zelan, Zahlan. It's a German word which means to count. And that's how we reach to the name of numbers and the integers. Now what happened? Now once everything started to settle down, we developed that we had certain amount of things and we have to divide it into parts. For example, if we had 100 rupees and we had our mother gave us 100 rupees and you are two siblings, you have to divide it in equal parts. Both of the siblings should get the same amount. When such needs started to come, there was a need of some more numbers. How do we divide things into equal parts, into few equal parts? How do we represent a part of the whole numbers or whole object or quantity? And that is when we started to get fractions, and similarly we reached to rational numbers. Now rational numbers is named as Q, which means quotient, right? And as we have already discussed, number system is extending. That means all the numbers which were natural numbers, whole numbers, are also rational numbers. Now, so far we have studied about rational numbers very, very thoroughly. We had several sections. Now, why it is called as quotient? Let me put some light on that. Suppose we have 4 by 6. Now, this is nothing but division, right? So when you divide, you get a quotient. That quotient can be in decimals as well, right? And that is why rational numbers are also sometimes represented by decimals, and that's how it is named as Q. I hope that makes sense to you. And that is what was number story. And after this, we had several number systems which was invented after this as well. We will be going to learn about all those in a while. So now, what is the definition of rational number? All of you remember that already, I know, but let's quickly go through it in a little bit of detail now. Okay, so any number which can be represented in the form of P by Q, where Q is not equal to 0. And the P and Q are integers. That is very, very important to focus on. Why? We will discuss that towards the end of this chapter. So where P and Q are integers, so such numbers are called as rational numbers. Now you might be thinking, why is Q not equal to 0? We have P by Q, right? And it is clearly mentioned P by Q, and Q is not equal to 0. What is the reason behind that? And many a times you might have been told that whenever you have 0 in the denominator or any other number like 7 on in the numerator, this division is not defined. What is the reason behind that? Did you ever think about that? If not, let's start thinking about that and discuss a little bit of why is q not equal to 0 in p by q. Okay, so we will try to understand with the help of division algorithm. Now, what is the division algorithm? When you divide any number, dividend is equals to divisor times quotient plus remainder. I am very much sure you are very clear with that. Let me take a number. Let me take an example. If you have suppose 15 by 4. Okay, so 15, the numerator is the dividend and 4 is the divisor, right? So how will that be represented? 15 is equals 4 times what will be the quotient. If you divide it, you will get to know quotient will be 3, and then here in this case the remainder will also be 3. So that is how we represent the numbers. And there's a very unique there is a term here where quotient and remainder are unique. What do I mean by that is, unique means to say that for a particular dividend and divisor, the quotient and remainder will only be one number. There is no other possibility at all. So to make it more appropriate, we introduce one more part to it, that let's call the remainder as R, and the quotient we will represent as Q. Already we have a divisor, so quotient we will represent it by T. Okay, so and divisor is represented by Q already over here. So we introduce one more criteria over here, that R is greater than or equal to 0 and it's always less than the divisor. When we have these two statements, we are 100% sure that this is unique. Now we will focus on why is q not equal to 0. Let's understand, suppose now for the time being we'll take the remainder as 0. Okay, to make it easier to understand. So if the remainder is 0, let's remainder is 0 and the divisor is 0. So let's take a number. You can tell any number. Okay, 11. So 11 over 0. Now if we have this number, what happens according to division algorithm? It becomes 11 equals, what is the divisor? Divisor equals 0, and quotient we have taken it with the variable t. Yes, we have taken it with the variable t. 0 times t. Now what should be the value of t so that 0 times t becomes 11? Is there any possible number? Do not tell me infinity. Infinity is a concept, not a number. We'll discuss about that after in further videos. But for now, is there any number possible, number which can be placed in place of t? Think about this. Yeah, you thought it right. It is not possible to multiply any number with 0 and get an answer as 11. Because 0 times any number will give you 0, and that means this equality cannot be satisfied and the division algorithm does not hold true. That is why q cannot be equal to 0, and that is why we always mention in the definition that q cannot be 0, and I hope that makes a lot of sense to you. Yeah, let's get going to the next. Now, so this video was just an introduction of what is happening in the class. So what will happen in this particular chapter. So let's have a quick questionnaire. So every whole number is a natural number. Yes or no? You can think about this, pause the video and try to answer all these questions, and I will discuss it after you have answered it. I hope you have paused the video and you have answered all the questions. Let's begin. So every whole number is a natural number. Yes or no? Yes, absolutely. 0 is a whole number, but is it a natural number? No. So every natural number is a whole number, but every whole number is not a natural number. That we have to be very much clear, because all the natural numbers are included in whole number. Let's move a step ahead. Every integer is a rational number. Absolutely. But why? So -1, can we write it in the p by q form of -1 by 1? It does not change the number, right? But we have in p by q form where q is not equal to 0, and obviously -1 and 1 both are integers. Yeah. Similarly, for any number, we can put a denominator 1 to that. And that is why every integer is a rational number. Now, can we say that every rational number is an integer? Absolutely not. As you can take an example, 2 by 3. It's a rational number, but is it an integer? No. After this discussion, I'll tell you one important thing, which is very much important in such type of question. Every natural number is an integer. Is it so? No. Or yes? Yes, that you are absolutely correct. Every natural number is obviously an integer. You can take any natural number, that will be an integer. Every natural number is a rational number. Absolutely yes. Every rational number is a whole number. This is not. Since every rational number cannot be an integer, and obviously whole numbers are a part of integers, so it is not true. Is 0 a rational number? Yes, absolutely yes. We can write always as 0 over 1. Now, mind it, my friends, we can write 0 by 1, but we cannot write 1 by 0. Can you think why? Because as dividend is equals divisor times the quotient. Now, what should be the quotient here to make it equal to 0? 0 equals 1 times 0, right? So the quotient is coming out to be 0. Since there is a possibility of the quotient, that is why 0 by 1 makes sense and it is defined as well, right? Let's move to the next things. I hope all the questions in this part is very much clear to you all. Now we discussed about rational numbers. Now you might be thinking, is there a possibility of rational numbers between two rational numbers? And I say absolutely what? Absolutely yes. But how many of them are possible? I say infinitely many rational numbers are possible. How do we find them? There are two methods. The first one is midpoint method and the second one is finding equivalent fraction. So we will start with rational numbers, finding rational numbers using midpoint. First, I'll show you with the help of diagram, with the help of the number line, I mean. Now, as you can see, we have to find rational numbers between 1 and 2. Now, here we have 1 and 2. What will be the midpoint? If I make it 0.5, as you can see, 1.5 is the midpoint of 1 and 2. That means when we found the midpoint, that will obviously lie between them, right? Now what can I do? I can further divide. Now if I divide it into 2 equal halves, I divide into 4 equal halves. Now as you can see, I have 1.25, 1.5 and 2.5 and further we have, right? Now can I divide it further? Let's see. I'll divide it to 1, 2, 5. As you can see, I have many more rational numbers between 1 and 2, right? All of them are decimal, so they are rational numbers. Now I will establish a difference between a rational and irrational in the coming videos. But for now, let's see. All of them are rational numbers. Similarly, if I make it into smaller segments, I make it into 1, 1. See? So that means if I can divide them into equal parts, if I keep on finding the midpoints, I can find lots and lots of numbers between 1 and 2. Let's try to work out how do we work out now. We cannot have this number line on our notebook, right? So detailed version. So how do we do that? Let's focus on that. So find 5 rational numbers between 1 and 2. So what do we do to find the midpoint? The average. Okay, so we find the average. So 1 plus 2 divided by 2, we get it as 1.5, right? So now we have 1, 1.5 and 2. Now is there a possibility of midpoint between 1 and 1.5? Absolutely. So that will be 1 plus 1.5 divided by 2. So that gets you to 2.5 divided by 2, and that you can proceed further, 1.25. Yes, so there lies 1.25. Similarly, if you find the 25, similarly if you find the average between 1.5 and 2, you will get 1.75. Yes, so we have found three rational numbers between 1.1 and 2. If we have to find further 1, plus 1.25 divided by 2. We'll get the midpoint once again. So 1 plus 1.2.25 divided by 2, we get 1.125. Yes, so we get one more value over here that gives us 1.125. Similarly, we can find between 1.75 and 2, or we can find one between 1.5 and 1.75, and this process goes on and on and on. So what did we discuss here? Any two numbers, find the average, right? Uh, how did we start? 1 plus 2 divided by 2, we got 1.5. Then between 1 and 1.5, 1 plus 1.5 divided by 2, we got 1.25. And then between 1 and 1.25, 1 plus 1.25 divided by 2, we got 1.125. And these numbers will keep on going and going and going and going, and we can find infinitely many numbers between two rational numbers. That is what we discussed. We can find infinitely many rational numbers between two irrational numbers. The second method is called as equivalent fractions. Now midpoint method becomes a little bit complex when we have fractions to deal with. Finding rational numbers between two fractions. So that is why we move our discussion to equivalent fractions. And I hope you are very much clear with equivalent fractions. What is the meaning of that is, suppose you have 2 by 3. Its equivalent fraction will be 4 by 6. Why do I say that? Because all the fractions which can be simplified to one particular fraction are called as equivalent fraction. Okay, I will write example: 2 by 3, comma 6 by 9, comma 8 by 12, and similar examples can be taken. So all of these numbers are called as equivalent fractions of 2 by 3. I hope that is clear. So now, using equivalent fractions, how can we find 5 rational numbers between 2 by 3 and 4 by 7? So whenever we are comparing here, it's a little bit concept of comparison, right? So whenever we start comparing, one thing we must be sure with, that we have like fractions with us. So first thing we do is we take LCM of these two numbers. So what is the LCM of 3 and 7? So they are both prime numbers. So obviously the LCM will be their multiple. So 3 times 7 is 21. So you must multiply 7 over here. Whatever operation we do in denominator, that must be done in numerator as well. Right? Whatever operation we do in the denominator, that must be done in the numerator as well. So what do we have now? 14 by 21. And 4 times 3 is 12 by 21. Right? So now once the denominator is same, we just need to look at the numerator. Can we find 5 rational numbers between 12 and 14? It's a little, we again have to go for decimal. So we will try to think of something. Can we make bigger equivalent fractions of them? Now mind it, equivalent fractions. That means our denominator is not going to change. Why? Because whatever number we multiply in the first number, that is 14 by 21, that same number will multiply in 12 by 21 as well. Let's see how do we proceed. So we will directly multiply it by 10. 10 is easier, right? So 14 times 10 gives us 140. 21 times 10 gives us 210. And 12 times 10 gives us 120. 21 times 10 gives us 210. Yep. So now can you find 5 rational numbers between 140 and 120? Absolutely yes. So 139 by 210. Then you can write 135 divided by 210. Simplification is your choice. 132 by 210, 131 by 210, and we want 5 of them, right? So we can take 121 by 200 of 210. So we have calculated 5, we have found 5 rational numbers which are between 2 by 3 and 4 by 7. What is the process we follow? I will repeat it. First, we made it into like fractions. Yes, because comparisons and operations on fractions, we generally take help of like fractions. And then what did we do? What we took help of? We found equivalent fractions so that we can have enough numbers between the numerator. So we've multiplied it by 10. Now, in some of the books it is mentioned you want 5 rational numbers, just multiply it by 5 plus 1, 6. If you want 10 rational numbers, just multiply by 10 plus 1, 11. That process also works, but why to take unnecessary formulas in our head? Just make into an equivalent fraction such that you have enough numbers between the numerators. That's all. And that's why if multiplying it by 10 is easier or multiplying by 6 is easier. You can choose what method you want to. So I always recommend to follow multiply it by 10 simply. You can find so many numbers. Now between 140 and 120 there are 19 different numbers. You can write any numbers which is between them. So 139 by 210, 135 by 210, it could be 130 through 33 divided by 210, and all these similar numbers. I hope this is clear for all of you, and I hope these two process make sense, right? So now most of the time we take help of equivalent fractions because midpoint method, it becomes a little bit complex when we are dealing with fractions. So that's your wish. Whatever you feel comfortable with, you can use that method. So now we found a lot of rational numbers on the number line. Yes, and we also found out that between any two rational numbers, there can be infinitely many rational numbers, no matter how small numbers you take. Now, I'll just ask you a question. How many numbers are or rational numbers can you find between 1 and 1 by 4? Obviously, infinitely many. How many can you find between 1 and 1 by 8? Infinitely many. How many can you find between 0 and 0.1? Infinitely many. That means whatever small interval you take, there can be infinitely many irrational numbers possible. And that makes it a really, really interesting thing to learn about. And that makes our number line much more interesting. So now the question arises, are there more numbers possible on this number line? Obviously, yes. What are they called? How do we recognize those numbers? Keep thinking. We will be discussing that in our next video. Until then, thank you from Apna Gurukul, one step towards success. See you in the next video. Until then, keep smiling. Jai Hind.